This is going to be practice problems 1 through 5 for module 13. So we'll start with number 1. And for number 1, we are given 2 charged particles. And Q2 is equal to negative 3.1 coulombs. And then these particles are 1.2 meters apart. And we are simply asked what is the instantaneous electrostatic force between them. So we just need to plug in our numbers. You will be given K. It's 9.0 times 10 to the 9th Newton meters squared over Newton meters squared over Coulomb squared. And then we will multiply that times each of our charges, 6.7 coulombs and 3.1 coulombs. We don't include the sign. And then we'll divide that by r squared. So 1.2 meters and 1.2 meters. So meters are going to cancel, coulombs will cancel, we'll be left with F, with newtons. And so the force, if we do our math correctly and with 2 significant figures, it should be 1.3 times 10 to the 11 newtons. Okay, now when writing our answer, then we do provide a direction, and in this case, since the charges are opposite, Q1 is positive, Q2 is negative, they will attract each other. So we would say the electrostatic force is 1.3 times 10 to the 11 newtons toward each other. Okay, so that is number 1. Number 2, we have 2 charges. Q1 is 0.32 millicoulombs. Q2 is 0.55 millicoulombs, and we are told that they have a repulsive force that is 2.5 times 10 to the 5th newtons. And it would be a repulsive force because these both have a positive charge, so they're going to repel each other. And then we are asked to find how far apart they are, so we're going to solve for R. So F is equal to K Q1 Q2 divided by R squared. So we just need to solve for R. Let's multiply both sides times R squared. Get rid of them over there. Divide both sides by F. So then we are left with R squared is equal to K Q1 Q2 divided by F, and if we take the square root of that, then we will get R. Okay, so now we just need to plug in our numbers. So R is going to be equal to the square root of 9.0 times 10 to the 9th Newton meters squared per Coulomb squared times our 2 charges, which were 0.32. They're in millicoulombs, so I need to change those to coulombs. so times 10 to the negative 3 coulombs. The other charge is 0.55 times 10 to the negative 3 coulombs. And then we will divide that by the force, which was 2.5 times 10 to the third, or 10 to the fifth newtons. Okay, so newtons will cancel, coulombs will cancel. We're left with meters squared, but till we take the square root of that, we'll just get meters. So in this case, R will come out to be so for R squared, I think you're going to get 6.336 times 10 to the negative 3. So then if we take the square root of that, you will get that R is equal to 0.07959, etc. And the units will just be meters. So we can have two significant figures. So that means that we would go 0.080 meters to get our two significant figures. Okay, so that's number 2. Okay, number 3, we have two particles that are equal in charge, but we don't know what that charge is. So we have Q1 and Q2, and they are 45 centimeters apart. So since we work in meters, we can go ahead and change that to 0.45 meters. So divide by 100 to get 0.45 meters. And we are told that the electrostatic repulsion is 2.2 times 10 to the 5th newtons. Okay, so they're the same. These particles are the same charge, but we don't know what that is. So we need to figure out what they are. So F is equal to K, Q1, Q2 divided by R squared. So we're just going to solve for Q1 and Q2. So we'll divide both sides by R squared. And then that gets rid of that over there. And then we'll divide both sides by K. Okay, so what we are left with then is that R squared times F divided by K is equal to Q1, Q2. So let's go ahead and plug in our numbers then. So R squared would be 0.45 meters times 0.45 meters, and then times F, which is 2.2 times 10 to the 5th newtons. And then we will divide that by K. And K is 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. So now our meters will cancel our newtons will cancel when you divide by this reciprocal, or when you divide by a fraction, it's multiplying by the reciprocal, so we would be left with Coulomb squared. So if we do this math, what you should get for, I need to check these significant figures, but let's see. Get 5.625 times 10 to the negative 6 Coulomb squared is equal to Q1, Q2. Okay, and so then since we know that these two charges are equal, we can just take the square root of that, and we get that what we get is 2.3717 coulombs is equal to Q1, and Q2 would be equal to the same. And with two significant figures, then we would say that Q1 is equal to 2.4 coulombs, and Q2 is also equal to 2.4 coulombs. Actually, this is 2.4. This is times. These numbers are times 10 to the negative 3. So this is 2.4 times 10 to the negative 3 coulombs. So you could also say that it's 2.4 millicoulombs. Okay, so that is question number 3. Okay, number 4 gives us 3 charges that are arranged in this way. This is plus 1.0 millicoulombs. This is negative 3.4 millicoulombs, and this is positive 1.0 millicoulombs, and they are 1 meter apart. Okay, so we have 3 particles arranged like that. And this says that none of these charges are forced to stay stationary. Explain why the instantaneous electrostatic force exerted on this particle is 0. Okay, so why is that? Why is the electrostatic force exerted on their equal? Well, the forces that are exerted by the other 2 charges are going to cancel each other out. So you're going to have an equal force. These 2 are going to be attracted to each other, so that's going to pull this that way. These 2 are also going to be attracted to each other. It's going to pull it that way, but their magnitude is going to be the same because the charges are the same and the distance is the same, so those will cancel each other out. However, the net charges acting on the other charge is not going to be equal to 0 because this charge will be acted on by this and this, but those are different distances apart because this is only 1 meter apart, but these two would be 2 meters apart. So they will not cancel each other out because they are different distances apart. And then of course these two are going to repel each other. This one and this one, because they are the same charge, they're going to be repelling each other. So they will repel each other, and they're farther apart from each other than they are from this particle. So the net the net charge will not be zero, and the charges, if they are allowed to move, they will move. Okay, so that's number 4. Number 5, we are given 3 charges. And this one is positive 1.2 millicoulombs. This one is positive 6.4 millicoulombs, and the last one is positive 9.1 millicoulombs. The distance here is 1.5 meters, and the distance here is 2.0 meters. Okay, so then we're really just going to do we're not going to do part B because we didn't get to electric field, so we're just going to do A. And A says, what is the instantaneous electrostatic force that is exerted on this particle? Okay, so we're just interested in that particle. So the 2 charges that would act on that particle would be this one and this one. So let's first do this one. So F is equal to 9.0 times 10 to the 9th Newton meters squared over Coulomb squared times times 1.2 times 10 to the negative 3 coulombs times 6.4 times 10 to the negative 3 coulombs, and then we'll square the distance between them, the radius, 1.5 meters and 1.5 meters. Meters cancel, coulombs cancel, and the force for those two comes out to be 3.1 times 10 to the 4th newtons. These are the same charge, so they're going to repel each other. So this particle is going to move in, as a result of this particle will move in this direction. Okay, so this would be 3.1 times 10 to the 4th newtons in that direction. Okay, then we can do the force for the other 2 charges. So now F is equal to 9.0 times 10 to the 9th Newton meters squared over Coulomb squared times 6.4 times 10 to the negative 3 coulombs times 9.1 times 10 to the negative 3 coulombs. then we'll square the radius, so 2.0 meters and 2.0 meters. So meters are going to cancel, coulombs will cancel, and the force that you get between this particle and this particle then is 1.3 times 10 to the 5th. Newtons. So then what direction will that be in? Well, these two are going to repel each other. So this part, the 9.1 particle, will cause this particle to go in that direction. So what we have then is, in terms of acting on that 6.4 particle, we would have a force in this direction of 3.1 times 10 to the 4th newtons, and then we have a particle in this direction of 1.3 times 10 to the 5th newtons. Okay, so to the right is positive and to the left is negative, so we would take 3.1 times 10 to the 4th newtons minus 1.3 times 10 to the 5th newtons, and what we end up with is a negative I think you end up with a negative 1.0 times 10 to the 5th newtons. So because it's negative, we can keep that negative there, and we would say that the force is to the left. Okay, I'm going to go ahead and run the math on that just to make sure that I had it correct. Yeah, so it comes out to negative 99000. And we can, I guess we can have two significant figures. So I guess we could say, I guess you could say 9.9 times 10 to the so this would be 9.9 times 10 to the negative 4, or 10 to the 4 newtons. And the negative sign again tells you that it is to the left. Okay, so that is it for problems 1 through 5. Those are the only ones that you will need to be able to do problems like that for the test on Module 13.